So it's a pleasure once more to have Lorenzo Gambagli with us for the third lecture of his great mini course. So please, Lorenzo.
Hi everybody again. Today we will continue from basically where we left, in the sense that we will assume that our hypothesis space is basically the space of a certain kind of deep neural network. And we will finally try to tackle the problem, the learning problem, in the sense that now that we have defined our basic tools, we will be able, I hope in this lesson, or at least in the beginning of the next one, to set up a full learning algorithm. So we will put together the loss function, the way to, the hypothesis space, the data set. We will subdivide the data set in a clever way so that we will have a fully functioning learning algorithm. And actually, what we will tackle today is basically the problem that we found after we have defined in abstract our learning algorithm, which was basically, if you remember, something that we derived from the maximum likelihood principle. And then we arrived at a loss, which was the expected value over the data distribution of our loss function that we have decided, of our probability of the model that we have decided, arbitrarily at the very beginning. Then we said that we could estimate this probability using some kind of criterion. For example, we could say that our probability of the model was Gaussian centered across a mean, or it was a Bernoulli distribution, and we were able to derive a proper loss function. And then this loss function was evaluated on each x, y data, and it was averaged out. And that was what we wanted to minimize with respect to the parameters that we have chosen to parameterize our hypothesis space. And this is precisely where basically the problem that we will try to face today. So the problem that we will try to face today is exactly this. We want to find the argmin, so the argument that minimizes this thing, where this thing is the estimated expected value of a certain loss function, which could be, for example, the cross entropy loss, or which could be, for example, the mean square error, evaluated on f and n. So between the loss function between f and n, which is our prediction parameterized by theta, and the proper yi, so the proper label that we have. Okay, so this is the problem we will try to face. As you can see here, there is h. So the hypothesis space is this mapping here. So how those theta are connected to our function. And actually, this hypothesis space is basically the way we will describe our neural network. So when we fix our neural network structure, we have somehow also defined our hypothesis space. Of course, there are also a little bit more something a little bit more subtle to fix, but for our purposes now, basically saying that our neural network is something that has two input neurons. The first layer has 3 neurons, the fourth 3 neurons, and the last one 1 neuron. This basically fixes our hypothesis space. Then we basically need to solve this problem. And if you remember, I told you one thing. I told you that this loss function very often is not, so this number here, which is a number, remember the loss function goes from the space of labels, from the space of labels in the space of positive real numbers, very, very often. And also is something you can also thought as something that goes from the space of functions to the space of real numbers, so as a nonlinear functional, but still this will be a number. So our problem is basically that this theta here, as we will see in a moment, is something we would like to compute the gradient of, but this is a non-convex function. And this is the whole problem with neural networks, because neural networks were actually a tool that was invented, conceptually was absolutely, is kind of oldish, I'd say, in the sense that already in the 50s and in the 60s, people knew those tools and were basically described almost very similarly in the very similar to how I'm describing them to you. But the very, 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 very big problem was that it was very hard to train them. And so basically finding this minimum, this proper minimum, so a minimum that could work well, was a very big problem. Okay, it was just, I mean, in basically early 2000 that we are able actually to have some kind of algorithm, of proper learning algorithm that were capable of exploiting the neural network as we do today. Now, of course, there are a lot of advancement in the sense that we have discovered lots of architectures, a lot of ways in which we can concatenate several neural networks somehow in order to properly tackle different tasks. For example, the very, very famous natural language processing task, which is more or less what you are trying to solve when you are talking with, for example, your ChatGPT or whatever. Actually, this is something that was, I mean, after the discovery of somehow the transformer or the attentional mechanism, it was something that it was, I mean, burst, like basically changed from completely. So the problem was much more easily tackled. And but still, of course, today what we will try to do is basically solve this problem with FNN, that is a feed-forward, fully connected neural network. So exactly the one I told you the last day. So let's now delve a little bit more into this problem, and let me focus on the fact that, as I told you, this theta is basically the collection of all WK B K from K equal 1 to L, where L is the number of layers in our neural network. Okay, so this is the collection of our parameters. We would like to compute their mean of this function with respect to those parameters here. Those parameters here are a lot. Let's try to understand how many are they. Actually, it's very easy because from one layer to another, you have the product. It's a matrix that goes from one space, which is of the same dimension of the layer. Let's assume that this is layer N1 and 0, and this is layer N1. Then, of course, all the possible connections, aka all the coefficient of the matrix of the linear operator that goes from this space to this other space here are N1 times N0. So in total, we would have Nk times Nk plus 1 plus the bias. So plus Nk plus 1. And this is something that you should basically do from 0 to L minus 1. And this number here, it's very large for let's say, usable neural network. In the sense that, of course, this is something I would like to stress. If you want to use a neural network with two neurons in the hidden layer, do not use a neural network. Use another thing, okay? But if you need to use a neural network, so your problem is highly dimensional, so all the features that I told you last day are present, then your neural network will very likely be quite big in the sense that you will very fast reach something around 10,000, 100,000, 1 million parameters. Because think about this, if your input space is an image that is 28 by 28, this first layer here will be 784. And if the next layer is more or less of the same size, because you don't want to lose nothing in the same computation, so you want to extract as many features as the space of your input, something not very common, but maybe if you want to shrink it and say, okay, it's half the size, then the number of parameters in the first transfer of information are 784 times, let's say, 300, which is basically on the order of 10 to the third and on the order of 10 to the second, so almost 10 basically to the 5, which is super large. Like, and this is just for a super silly problem, because the problem I told you is nothing compared to the real world problem. So what I want to stress is that this space here is huge. You are computing the gradient in a space that has billions of directions. And this is something that will basically introduce a lot of challenges, lots of challenges. So the first problem that we will encounter is that this space here is huge. So the dimension of theta, huge. The second thing that we will encounter is that it's actually also the first one that I told you, that is not convex. Which basically will imply two things. First of all, difficult to find global minimum. And second, there might be not unique solution. Okay? And those are the two things I've already mentioned. And then another very important thing is that as the network grows very fast in dimension, if you remember the MSE decomposition, we will very likely end in this part of the spectrum here. So we will very likely end in the high variance part, which means that our result is very likely to largely depend on our data set, which also means that we are very likely to overfit our data. It means that in our data set, this is of course a very simplified thing, but it's worth knowing. If our data set is something like that, and our test set is something like that, that will be a little more extreme. Okay, we are very likely to find this solution instead of this one. Okay, so that's the problem we will encounter. Another problem that we will have to face is it's deeply connected with the fact that all our very nice assumptions are not available, in the sense that our data distribution is not known. And therefore, it's very unlikely that we can sample from our data distribution. And therefore, the dimension, so P is finite. So we have a fixed amount of data we could exploit in order to learn in order to find this proper minimum. Okay, so those are the challenges that we will encounter. The main ones, of course, there are 1,000 ones, but we will spend here like 3 hours. How can we solve all those problems? We will basically solve all those problems starting from the ones that actually, surprisingly, will not be very much of a problem. And for example, the fact that it's not unique, we lose a little bit of theory, but still it's not that much of a problem. Okay, what is a problem that it's difficult to find the global minimum. But if you remember, if you think about it very deeply, the global minimum is not exactly what you want to find. Why? Because this solution here lies in the global minimum. Why? Because the loss of this function here on our dataset is 0. So this is something you don't want to have. So it's not that much of a problem. Actually, there are lots of very interesting results on how neural networks are capable of generalizing how neural networks are capable of avoiding this kind of solution, even when they are very largely parameterized. But this is something that isolates from the scopes of these courses. But still, what happens is that what we will find is for sure a point. Is for sure. It's very likely a point that is not a global minimum. And of course, I expect that due to the large dimension we live in, it will be a saddle point. So very likely, our point will be something along which, on which a lot of directions are like that. And there are also a lot of directions that are like that. So in this space here, what we have are a lot of very strange behaviors around our global minimum. Each one of them is basically the direction in our highly dimensional space. So those are the properties of the minimum that we will find. But we want to find one because we will start for sure from a terrible point. Actually, this is something that has some kind of caveats. This is just to tickle your curiosity. Interestingly, if you pick a very large neural network, very large, like basically infinite, you are very likely to be very close to the solution of your minimization problem. So we will, and what happens is that your shift in a limit, we will not try to address now, but this is just to tell you that, the research line in this field are infinite, okay? For what concerns us, this is the properties of the minimum that we want. So there is a subtle point, but basically lots of them are proper minima. And we want to find it because we will not start from a proper. So we will solve those problems in this way. So no, we're not infinite. So this problem here, let's try to change it in the sense that the only thing we will calculate is non-convex. So if we are not smart enough, we will find the first, very likely terrible, local minimum. We want to find a proper local minimum. So this is another thing that is very tricky. Our neural network will definitely arrive in a non-global minimum, but it will be a local minimum that has, I would say, a lot of directions along which it is a minimum. Okay? So those are the property of the minimum that we will reach. So the non-convexity is still something we need to tackle. The thing that theta is huge is something that we will tackle, but we will, I will spend only very few words on that, in the sense that a very huge advantages that neural network have is that the gradient operation is something that can be easily computed on a GPU. And it's just thanks to a lot of advancement, technical advancement, that we are capable of basically computing this gradient with respect to our very difficult function and evaluate the gradient in lots of points very fastly and in parallel. And this is something that is due to, something you can actually do yourself if you implement your code in a GPU, in the sense that it is not a lot of work, a lot of computational power, it's not spent in the CPU, so on operations that are somehow sequential, but will be spent on operations that are parallel. And this is something that will happen on your GPU. So that's why very often neural networks are implemented on GPUs, because part of the possibility of computing this gradient in a very huge dimension in a time that is still computationally somehow attractive is something that is due to our capabilities of implementing these operations on a GPU. How much is the difference? It's worth trying. It's like super large, in the sense that you go from a gradient that can be on the orders of, I don't know, maybe let's say, a full training around minutes in something that goes in seconds. So very fast. And then this is something that we try to tackle with how to compute the gradient. So this problem here, it all lies in, we will try to address this, and so we will find how to compute the gradient in a neural network. And this is something due to the backpropagation algorithm. This non-convexity is something that we, so this is, I will tell you more or less how we compute the gradient. Of course, I will not spend words on the implementation and why it is very efficient and so on and so forth. But I think that some of you might have already heard the word backpropagation. And if not, as soon as you open anything connected with neural network, you will find it. We will see that it's a way of computing the gradient in a single pass. So evaluating somehow our neural networks layer by layer in a very efficient way, somehow, okay? This other part here, so the pattern is non-complex, is the stochasticity of the gradient. So we will use a stochastic gradient. And the fact that P is fine, that P is, so we will add noise to our gradient in order to find the minimum that with the characteristic that I told you. And then the fact that P is finite is something that we will exploit in order, this is a problem, of course, and it's always a problem, but we will see how to use this. Oh, I also forget to write down the high variance problem. So this is something we will try to use and try to be very smart, in using it in order to solve this problem here. So this thing here is something that we will tackle with regularization. And it's something that we will at least in this curve, is something that we can explore as much as you want, but still, I think that one way in which we can solve this problem is basically by using in a smart way our data set. So with the validation set. Okay, so we will start with backpropagation, and then we will go through the stochastic gradient part, and then we will end up with how to properly use our data set in order to find a solution that is not in the space of high variance somehow. So we will try to control the complexity of the space of functions we are exploring with our parameterization. So let's start with the backpropagation algorithm. If there are no questions, and what I try to say, what I try to explain is the core idea of the backpropagation algorithm, because I think that this core idea is kind of, illuminating in the sense that you will find that, also implementing it, it's not that hard. And I personally find, this something very useful to start making your head up on neural networks. So to become more expert with the formalism of layers and so on and so forth. So the idea of how to compute the gradient is something that we will try to convey in a qualitative way. Okay, but still, I hope that will convince you. So, which is the idea behind the way we compute the gradient on a neural network? We have this huge space of functions. So we have this huge network very often, but for our purposes, let's consider this one. So this is n0, this is n3, n1, and n2. What happens? Usually what happens is that you have your x, you put here, and it will return you two activity at the end, right? After every passage. And then you will compare those activities with the one that you know are true. So the one. I hope also that during this explanation, you will also understand very well every concept that we have introduced. So for every xi, and we will have a yi, and we would like to compare this. The comparison, of course, is due to the loss function. So for example, let's assume that, let's focus on those two things here. Let's assume that the last ones are like 0.2 and 0.8. And let's assume that you will like 0 and 1. So we have a classification problem. So those are the y that you want, and those are the y that you get. So y1 and y2. The thing is that you would like these to become smaller and this to become larger. Now, let's understand how this activity changes. We will have indeed in N2, so we will now focus on, we shall now focus on this part here. You will have that the activity on this neuron here is due to the combination of, let's say, three conceptually different things. The connections, W311, W312, and W313. Due to the activations that you have here, so basically, if you want to recover the interpretation of the feature extraction, the features, so the components along certain directions that have been extracted, so the components of the first representation after the extraction of those features is a scalar product that results in certain components. And each of these components is then filtered out using the nonlinear function, and you get scalars, which are somehow the relevant feature that you have, are connected with the relevant feature that you have extracted at layer 0, 1, at layer 2. Okay, so your activity here, so the value that you read on each neuron here, is something that we will call Z1, Z2, and Z3 for simplicity. So this here also will have its own bias, B3. So 0.2, let's say 0.2 will be equal to, okay, let me, I hope that this somehow is legit, so let me do this. Now we are going up. So 0.2 is the result of W11 Z1 plus W12 Z2 plus W13 Z3. This layer 3 plus B1, 3, and all of it with a nonlinear function. This is the activity we'll have here. Okay? Remember that the activity here is the same thing and the same thing and so on and so forth. So how can I augment how can I diminish this value? I can diminish this value acting on three things: the bias, the weight, and the activation. Actually, in the linear regime of this, so around this activity here, the change, so if I linearize this function here, I will get that the variation. So how can I act on that? So now let me release this. So I can vary, so I can change W, for example, W11. Let's focus on the first neuron of the third layer or of the second layer. So this would be W311 and we have Z1. Let's assume that we change W311. This change will be proportional. Why? Because we will have the derivative of the sigmoid evaluated at this point times Z1. Or we could change Z1. And this will be proportional to W11. Okay? Or, of course, we could also change the bias. But let's now, for this moment, ignore the bias. And let's focus on those two things, because this is really the core of the backpropagation algorithm. So the idea is that let's assume that we would like to change this. If W, we will construct somehow a matrix like this. And W11 can be positive or negative, and so it can be Z1. If W11 is positive and Z11 is positive, we would like this to diminish because we compare this with 0. Then, of course, we will have to, if we want to change this, we will have to decrease W11. If W11, I mean, the same holds true also in the case that is negative. Okay, we will have to decrease it, increase it in absolute value, but decrease it. If Z1 is negative, of course, if Z1 is negative, then if W11 is positive, we will just augment it. And of course, the same is for this case here. So for the case of the weights, how to change the weight is already defined by basically Z1. And there is only one way in which you can affect this by changing the weight. Okay? What about this other part here?
Can you repeat a little bit this? Because I got a little bit confused about this, how the different weights are interrelated with the variable. So the W0 will be the first step, the first W110. Is this
0?
Is the first interaction? What?
Okay, so what I'm describing here is how to compute the gradient in this case. And the gradient is, to me, is something that I will use on how, in order to understand how I need to change my weights inside my network.
Yes.
And here I'm trying to focus only on the how to change this activity, this fictitious activity, which is 0.2, 0.8, in order to be like 0 and 1. Because this is how I would like this activity for
yes.
by a small amount W, B, or let's say Z. Let's now focus on W. If I focus on W, if I want to change this, I will just need to change this W by a fixed amount. And the way in which I can vary this is completely determined if I have Z1. Okay? Because I know how much the activity Z1 reverberates on this node here. And the same is true here, so for W to 1. Again, if I want to increase this in the same way, if I know the value Z1, then of course this is the, I mean, this is something that I already know. What about Z1? The idea is that I could also change that Z1. But if I change Z1, of course, then Z1 should, for example, change by 2 different amounts. It could change by 2 different amounts. Indeed, let's now focus on Z1. Z1 should have a delta Z1 due to this path here, 1, 1, which is how much it should change fixing this in order to decrease this value. And it will have a delta Z 1, 2 that it should make in order to maximize this value, so to increase this value. So that Z1 could change, I mean, has 2 variations that it needs to, somehow it can do. Delta Z1 and delta Z1 and delta Z2. Okay, this is a terrible name. Let me call it delta Z11 and delta Z12. So the variation due to this path and the variation due to this path. Let's sum those variations. Somehow we average those two variations out, and we will get delta Z1. So we will say that delta Z1 should vary by this amount. And now this is the core of backpropagation. The idea is that we knew delta. Let me call this the L neuron. So XL1. Maybe let's call this activity with ZL. We know this variation, this is 0.2, and we know this variation, delta ZL2, which is again 0.2. And we know how to reverberate this variation in the weights and then in the activity. So by fixing the weights to the value that it's written here, we don't care how this value, which this value is. We then can compute how the neuron on L-1 should change. So now we have a target for this neuron here. And so in these other three neurons here, we will repeat the process. So now that we know how we should change this neuron here, we can reason in the same way and try to evaluate how W211 should change, how W212 should change, and how W213 should change. And then we will extrapolate delta ZL-2, and so on and so forth. So we will back propagating our difference here through the whole network until we arrive at the input. And then the input is fixed. So there is no variation with respect to the input. So the input will be just evaluated. And then we can do this. So we have one input, one output, the expected output. We compute the difference in this way. And this is the difference because I have assumed that my loss is basically just the absolute value. But if it's not the absolute value, it will be just the difference multiplied by the derivative of the loss. But this is just a small complication in the whole process. So this variation here rebounds on the variation here. And so on and so forth. And the way this variation is transferred is due to the weight matrices. So somehow there is the transpose of the weights that does the job of back propagating the variation from one layer to the other one. And if you are familiar to network, this is something very illuminating because somehow the transpose of the network shifts the variation backwards. And if you are familiar to topology, this is something that is also very deeply connected with the pushback and with the pullback and push forward operations. So somehow what we have discovered is that as soon as we have unexpected output, we can understand how we should variate every weight, and then how we should variate by fixing the weight, how we should variate every neuron's activity. And we just backpropagate this until the input. This is the core idea behind backpropagation algorithm, because it lets you in one pass to have obtained how to variate the whole network. You can accompany this, so you can exploit this also with advanced technique on how to compute this sigma prime, because let's assume that sigma prime is always the same across the whole function. Then there are very clever techniques that let you not to always compute this sigma prime, but to have it ready for you every time you need it. The so-called there are techniques that are used, and I will not delve deep into that, which will let you to basically go very fast down in terms of number of computations that you need to find how to variate every connection in your network. Okay, so as you see, the delta, so on the output, which is equal to the epsilon predicted minus the epsilon real, so yi, and this epsilon predicted is basically my f and n of xi. With this delta out, I can compute how to variate everything in one pass, which is a super impressive thing to me, because with only matrix multiplications, somehow, you are capable of computing the gradient of knowing how you should variate every link in the network. And due to the fact that this way this matrix multiplication is very efficiently implemented in your GPU, that's you are capable of evaluating the gradient of your function at a given x in a very, very fast way. And if we have different variations, we will sum them. The idea is that if we have 10 different data, so we have x1, x2, x3, x4, and so on and so forth, we will evaluate how we should vary each connection according to each data, and we will average this out. So the way in which we will train our network is somehow something that is a sequence of update that goes as follows. Now that I hope that I have convinced you that we are capable in a very efficient way to evaluate numerically how we should change. So numerically, not analytically. Remember, here everything is numerical. We just propagate backwards. We are capable of evaluating the gradient at a certain point. What I basically will do to train my network is that I will change. So let's assume that we are at f of t. Let me call this epoch t, where t goes from 1 to capital T, which is the total number of epochs. We can construct something that is a way of updating our weight, which is the following. The weight at the next step will be the weight to the parameters of the step before minus alpha, the gradient with respect to theta of our loss function averaged on our data set. Okay? Because this we know for each data how we should change every weight. So we will collect all these variations and then sum them and then average them out. So if according to x1, let's assume that we are focusing on this weight here, weight here, we should change delta W1 due to x1, delta W2 due to x2. Basically, what we say is that, okay, let me average all those things out. Remarkably, this thing here, it's a gradient, that it's not the, not remarkably, this gradient here, it's not the perfect one, right? Why? Because the perfect one somehow should be the one averaged over all the data distribution, but we don't have it. We just have our data set. So we'll estimate how to change it based on our data set. This is something that is a very clever way to change our weights. But we still have the problem that, we will, for very likely, we are not doing exactly the exact gradient because of the fact that we do not have the full data distribution. But if we have enough data, this will be almost like the proper gradient of W, in order to maximize the likelihood, or in order to minimize the Kullback-Leibler divergence, or in order to minimize the cross entropy. The thing is that reality is a little bit worse than that, and it's not convex. The problem is not convex, so we will have a lot of bumps and a lot of problems. How can we solve this? We could think about adding a noise. if we add a noise, maybe we will not get stuck in a local minimum. That's the idea. We could, in principle, add a noise that is a random noise, so it's a Gaussian. We could add a noise that it's not a Gaussian, but it's not correlated, and so on and so forth. We could come up with a lot of ideas. Turns out that one of the best way in which you can solve this thing here, so in which you can introduce noise, is let your data to introduce the noise. How can you do this? This is the average over the whole data set. So the average over the whole data set is something that if D is super large, will basically be almost like the proper gradient. So the proper direction you should go. But if your data set is super small, the direction you will compute, so the average gradient will be a terrible one, very likely. So let's assume that we have our data set, D, and let me partition the data set in this way. As the union, this is the joint union of different BJ, which goes from 1 to a number that I will call MB. Those BJs will be all inside D, okay, included in D. So what I'm saying is that I will have my whole data set and I will partition it, okay? I will divide it in several non-overlapping sets. Of course, those sets, each BJ, if I compute the gradient with respect to the average over a single BJ, it will be a worse estimate of the proper gradient. So I will not move toward the direction of the minimization, but towards somewhere that it's not exactly the minimization, which is basically the same result as introducing noise. So the idea is that I will update my weights, my parameters, not after each evaluation on the whole data set, but after each evaluation on every partition. And this partition is called batch. So what we are doing is a batch stochastic gradient descent, because the stochasticity will be induced due to the fact that we are estimating in a wrong way our proper gradient. And this turns out to be incredibly effective, incredibly effective. So the thing is that as soon as you have BJ, usually what you do is that you fix, and not only this is a very nice way to introduce the gradient, to introduce noise, but it is also a very nice way to implement your algorithm when you have a very large dimensional input. Why? I hope it will be clear in a second. Let's assume that you have, usually you fix either NB, so the total number of batches, or you fix the batch size. Of course, NB and the batch size are basically connected to this. So if you divide the P with the total number of elements with respect to the batch size, you will end up with the number of batches that you have. And so what you get is that basically if you fix BS, you can then construct an algorithm that is the stochastic gradient descent that basically works as follows. We will have now two indexes, P that goes from 1 to the total number of epochs. We will do for J that goes from 1 to the number of batches. We will update our parameters. Okay, let's assume, yeah, we will update our parameters in this way, like M, B, sorry, that's a terrible indentation. Maybe I can write this here. So, as you can see, for every t and j, what I get is the fixed update. So for t equal 1, I have the first update if I have j equal 1. So I will start from 1 here. So if j is equal to 1 and this is equal to 1, we have theta 2 equal to theta 1, which will be theta of n b t minus 1 plus j, minus alpha, the gradient average over Bj. That's the stochastic gradient descent algorithm, where the stochasticity is introduced by the batch, with the batch method, with a batch size. And so this thing here basically is this 1 over the batch size. You can think about this now. Of course, this is all divulgative. Of course, if you look carefully, it's not exactly that, but to understand this is basically that. Theta and b times t minus 1 plus j. So f I have already in this point here. Y. So that's basically the average of this gradient here. Okay? That's the stochastic, the batch stochastic gradient descent. As I was saying before the lesson start, before the lesson start, I was actually saying that this method here, it's a little bit too simple in the sense that if you do exactly this, you will encounter again a lot of problems. And so there is this whole field of accelerating gradients, which is something that actually remarkably, from a mathematical point of view, and for mathematician, is something that has been is started in order to reach faster convergence on convex loss function. But the same technique can be also used in order to basically improve convergence on non-convex functions. So there is this somehow confusion, again, as you will find that this word is full of like confusion and full of different way of naming things and so on and so forth. Those are all accelerated gradients which improve this. And a very famous gradient is what is called Adam. And all those stuff here can be thought as something that is basically a function of this. So we basically change this again on a given batch. So it won't be exactly the average of the gradient. It will be something more complicated, much more complicated, because you would like to, for example, avoid things like this. So in the space of theta, maybe what you are doing is something like that. And you know that you would like to do something like this. And so there are ways in which you can reduce this variation here, introducing, for example, a momentum in your algorithm. Or there are some things that are more connected with, for example, the fact that very likely, if you start your algorithm, you'll be in a very bad minimum. So, or in a very bad position. So it's better to be fast at the beginning than it is at the end. And so this parameter here, alpha, which is called the learning rate, which basically leverages, weights how much you should vary your parameters. If alpha is 0, and you have no variations, this learning rate here can be adapted. in order to be fast at the beginning and then very slow at the end. And also other techniques like that, for example, adapting this with respect to the memory of all gradients with a certain parameter and so on and so forth. The algorithms can start being very, very tough very fastly. But the idea is that Adam and also LMS Pro and also Momentum, which is the simplified version, maybe simpler. If you want to start to understand those accelerated gradients, if I were you, I would start with Momentum. Especially if you are a physicist, it's like it's very, very natural. And basically, those techniques here can be used to properly write this F. Now that we have developed our way of changing the weight in our method, we can try to tackle the last, somehow the last problem, which is the fact that our neural network, very likely, if you let it run, if you let it optimize, and this optimization process is also known as training. If you train your neural network, it will reach a solution that is another. So you will find this thing here instead of this thing here. Why? Why it's very likely that this happens? Because if you remember, there is the universal approximation theorem going on. So your neural network, if they are large enough, they are capable of finding this solution. We are definitely in the case where our hypothesis space is like that, and our target function is in the middle. So our target function is definitely in the middle, but still there is also another function that we don't want very likely, which is the function that basically has L on the data set equals 0. So the zero loss function is also inside this, which is a problem, a very big problem, because if your algorithm is perfect and you have 5 data, you will reach this. If you have 10 data, you will reach this. Of course, if you have an infinite amount of data, this function here slowly shifts to the target function. That's the idea, more or less. So if you train on a very large number of data, what you will find is somehow this, which is something we could also have, I mean, we could also delve into this if you want, but you can basically do exactly the same graph that I built for the MSEs, for the mean square error, also for your train loss and your evaluation on your test loss. If you remember, it's the loss function or the mean square error in our simplified case, evaluated not on the data that are inside B, but on data that are outside the B, so that you have not used to find your solution. Though you can also do like those curves here that are called learning curve. I will send you some of those learning curves that maybe are useful. But still, the idea is that this function here is inside, is possible, is feasible, is something you can reach with your neural network, and you don't want this. You would like this. So you are in an overfitting regime, very likely. You will be very likely in an overfitting regime. How can you solve this problem? We can solve this problem still working with a fixed amount of data, ironically, by splitting our data. So our data set will be divided into DT and B. DT is what we will call the train set, and B is what we will call the validation set. What I assume is that there are also some data that I never mentioned, because I want you also to think about them in this way. They are like away from the very beginning of the moment you are starting to think about your problem, which is the test set. This is something I always take for taken away. So something that you have, but you never use. And I never mention it because in every time you use your test set, you need, I mean, at least from a moral point of view, you need to stop using your computer. You need to stop using your learning algorithm. As soon as you evaluate your learning algorithm on the test, then you have to stop. So you close your computer and you say, this is my solution. Because otherwise, as we will see in a second, there will be no difference between those two things. Okay. So I hope that now that I introduced everything, you will also understand better what I said before.
So can I ask a question? So for example, if I have a time series and I want to separate of a given period, I'm trying to get the parameter over the whole period. A way to separate the train set and the validation set will be, for example, to take alternate alternate data, like to construct, for example.
Usually the better thing to do is to have different because if you have one single string of time points,
yes,
it's kind of very likely that you will overfit. So you have to be smart in the sense that, yeah, I mean, naively, what I will do is like pick few of them,
exactly.
then leave them outside.
Random. Yes. Okay.
I will do this at random. But if you fix another rule, okay. The thing is that the idea is that you have your data set.
And how do you do with the missing one? Do you do some interpolations? Do you?
No, with the missing one. Oh, you mean the one that you are not using?
Yeah, exactly. The one that I use for creating the validation set later, or.
Well, I mean, you could come up with a kind of an interpolation thing, but I don't know if it is like maybe if it's the right solution. The thing is that if you have a single temporal thing,
yeah,
it's tough, because if your temporal stream is very long, then and it's something that it goes from it's something that is due to the same process. I'm not an expert on time series analysis, which is something that with deep neural network, with deep neural network, you will not do. You will use recurrent neural network, long short-term memory network, transformer network, so different kind of network. But still, what I mean, usually if this is very long, you can kind of split it in several things, and maybe you want to find something that is general. This is one way which you can use your full
like some stationary process. You can do it because then it repeats, and you will use each time series like
like they are already on the attractor, and so what you say is that they are already on the attractor, so I can evaluate the property I want on each point, because I'm always in the attractor, because maybe what you want to find is the attractor. Or maybe you can, but I mean, interpolation, I don't know, it sounds something that I don't know. Maybe it's something you can do, but I don't know. I can ask to someone who is more into that here. Something in my head is saying to me that interpolating might not always be the proper thing. Maybe you can treat them as missing data, and so you can just skip it. So you can just say that your gradient will not be dependent on the difference between the proper function here. I would say something like that, which is common sometimes. Very often you have missing data and you have to deal with them. There are ways in which you can account for them, but still, interpolation is a way. But still, if you are interpolating, definitely you have to take into account that your learning algorithm then includes also the way you interpolate.
Yeah, actually, because when we deal with, for example, climate data, it's not just one data missing. Sometimes people go to vacation and they don't report the data. So we have at least sometimes 2 weeks missing data. And it's a pity, because maybe we have a time series of 9 years, but then in the middle there are 2 weeks missing data. And so usually we cut and we say, okay, instead of 9 years, it takes 6 years, you know, like you cut it out. But instead, as you said, it might be a way to using it, just neglecting that part.
Also, I mean, another is treat them as two different series, or S1 and S2.
Yeah.
Because the function should be something that either work if you, I mean, if you start from here or from here. So if you start from d equals 0 or from d equal 20.
Yeah, in this case, the process is not exactly stationary because there are variation. You know, there are some recurrent seasonal effect, but there is El Nino, there is something that is not exactly the same.
Yeah.
But it's yes, but you say one could just ignore as a variation in that period.
I think that definitely if you have your if you, for example, if you have somehow let's say a recurrent like neural network, then the network will be capable of generating its own time series step. So here you have something to compare it. Here you don't. And then also here you have your generated output, which would be the one of your network, where the input would be its older one. And then you keep on comparing. So it will, if I were you, I will let my function interpolate. I will not interpolate for my function. If you interpolate, then of course you will be, I mean, you'll be introducing the bias of your interpolation, which maybe it's not that much. And so you can do something like that. The way in which you tackle the problem of fitting with neural networks time series is very different from the one that you have if you have a deep network, a feedforward or fully connected deep neural network. Because there the problem is much more similar, as you were noticing, to the problem of finding somehow the derivative of a dynamical system that lets you integrate. So there are neural networks that are capable of doing that, or learning algorithms, I would say, that are capable more or less of doing that. If you're interested on that, I can definitely send you a lot of stuff. Yeah.
Yes.
So as soon as you have your X, Y, you will basically do something like that. You will have the train center, and then you will have the size of the validation. In the sense that you will try to estimate, like this is again a very simplified picture, but the idea is that the complexity of the model is something that you can also think, and this is also something that I really, I mean, want you to, I would like you to try in your own. So by really plotting the function that your neural network is representing, maybe during the training, which is something you can do for simple functions and for simple scenarios. But still, what you can assume is that by basically during your epochs, so at each epoch, so at each evaluation of the whole data set, not at each batch, at each epoch, you are basically exploring different regions of the space of function. But is this different from doing this at each batch? It would be a little bit more at random, but in the sense that at each step, what you are doing, now that we are using batch gradient descent, we have, remember, one step for each batch. At each batch, you will be basically exploring different function and more complex one. Why more complex one? Naively, because you will reach a moment where you'll be overfitting. That's your assumption. And so what happens is that you can here have your training epochs. So the structure here is known. I will have my data set there, and then I will have my training set, which is again a collection X, Y, Y, I from 1 to the size of the training set, but it will ignore it. Here, what I will do is basically I will have my training set, my validation set, and what I will assume is that T, so epochs, are somehow a measure of complexity. And so what I expect is that during my training, if I estimate the distribute the loss of my, so the loss outside the point that I have used in my training set, I will have a behavior that is almost the one that I show you in the MSE variance decomposition. So the loss, the MSE, let me call it, it would be the loss, but the MSE on the validation, to me, at this level, is an estimate of somehow the expectation over P beta of F hat of a given D minus P. That's the idea. I will try to estimate this, which again is hopefully an estimation of the expectation value over P beta over the expectation value over the double distribution of F, D, and so on and so forth. Okay. Unfortunately, not always you are capable of properly estimating these. You can do estimate of that using methods, but we have just mentioned them, and so we will not delve into that. So the idea is that you would like to estimate this only with that, which is the test, what you do usually with your test. But let's ignore the test and let's estimate this with other data, the validation data, that I'm not using in my algorithm, in my learning algorithm, in the sense that I'm not using them in my gradient descent algorithm. So my batch size will be something that I will fix, and will fix the number of batch inside my training set. So those validations are something I only use to evaluate my loss on. So I have basically this behavior here in MSE, and so I will keep track of two things. I will keep track of the loss. So sum of I of L of, okay, let me do this. I hope that you have understood this division. I will keep track of this. The train loss, which is the sum over over X, Y belonging to BD of L, of F and N, X, theta, Y. And this is something that is a function of T. Why? Because this is a function of T. Actually, this should be a function of T and J. Remember all the epochs and all the, like every epoch and every batch step. So here I am using a little bit of notation, but basically this T here is somehow the step. So okay, let me do this. Let me go to the step K. So K will be NV times P minus 1 plus J. So this, the loss is a function of K, the train loss. Okay. This again should be average, so 1 over the size of the V somehow, but it's not relevant, it's a number in front of it. So its behavior will not change. And then we have the validation loss, which is again a function of K, and will be equal to 1 over the size of the validation of the sum over X, Y belonging to the validation set of the loss function. I'm doing this terrible L, which are like alphas, of F and N of X theta K therefore, I have to I can keep track of those two things. I can expect a behavior that is like that. My training loss. So let me do my training loss in red. I hope that you can see it. You see it? You see it? Not that much.
Not so much the red. Yes.
Maybe with orange, it's better. Okay, no problem. Let me do this. So my trade loss is something that I will expect we do something like that. This is my train loss. Why am I very like drawing it fluctuating? Because it's a stochastic thing. And my validation loss is something that I expect will do something like that. Maybe it will be also higher. So this, that would go, sorry. So this would be my train loss. And this would be my validation loss. So at a certain moment, my validation loss will increase. Why? Because I'm overfitting and I will be deeply inside the high variance region. Okay, so my complexity of the model, which was something very abstract at the very beginning, was very conceptual. Now we are saying that our complexity of the model we are representing, so our f hat at each t, so the model we would get if we would stop our learning algorithm, will be something that is basically tracked by the validation loss. So it will be something that increases because here we are in our overfitting scenario. Here we are in our downfitting scenario because the validation loss still can decrease. So I can still do better than what I'm doing, even outside my data set. So my test error, my out of sample error, how is it also called? So the one that I called MSE, the proper one, so the expected value over everything somehow can still decrease, which is something that is good per se. Now there will be a spot here, which will be the perfect one. So more or less in this region, I should stop my training. As soon as my validation loss reaches this level, I will stop my training. So my test loss will not reach this minimum. And my validation loss will not start increasing. So that's how I can guarantee empirically that I will not be inside the overfitting region. So inside the overfitting set of parameters. So here my f hat of, let us call it of f and hat of x, comma, theta, sorry, this is k, of theta k star will be the proper one. Will lie if I will. My assumption is that now, if I compute the test loss, now that I've stopped everything this end, my test loss is something that will be a point. Maybe you are not seeing here. So my test loss after that process which is an estimate of the expected value over p data of f minus t squared somehow, not square, but again, square is how it is properly defined, but there I can basically say L of f hat which is again, with one realization of D, it's also my estimate of the expected value of the data and of the expected value of the whole distribution. This, which is the sum, 1 over the size of P, the sum over X, Y belonging to P of L of F and M hat now X theta of K star Y. Why am I doing this square here? Because I want you to have in mind the bias decomposition, which is something very intuitive if you have this square here. But still, I mean, like my test loss, of course, will be the proper one, will be the loss one. So here, this thing here will be a point in my, which will be almost in a K, which should be the evaluation at a K star, which is somehow in relation with a certain complexity. And so I hope that I line here also in the test loss, which is an assumption. Okay, but usually that works pretty well. So now I hope that everything is starting to make sense, because we are putting together every aspect. We are seeing how actually everything is computed like for real. And now I don't have time. And so in the next lesson, I will write you down the full learning algorithm that we have everything into account. Okay?
Okay, thank you. Thank you so much. Great lecture. If you can also send us beside the notes some material that we could read, because I think you convey very well this idea, and I think that it also happened in our data fitting, similar things, because overfitting is so easy to get, as you say. No, it's very easy.
Especially with proper ML task, it's very easy, very easy.
Yeah, and so
I will send you, I mean, for sure, I will, like, my favorite book in the topic is Deep Learning by Goodfellow, Benjo, Corville. I will write you everything. I think it's like the Bible. It's what I used in back in the days when I was a student, and what I've been using since then. There are thousands of very nice books. Lots of them are more on the statistical part. Lots of them are more on the network side part, and so on and so forth. So, but yeah, I try to make a proper sum up so that you can expand. Definitely never underestimate the power of YouTube, because like the backpropagation algorithm lesson is basically one that you can find also on YouTube and a channel that I will send you, which is by this amazing guy, who is a lecturer at MIT, and also Google. Still, it's a pretty good friend if you find something that has the references. I want you to, I mean, I want to warn you to, because it's a topic that is exploding, and it's also a very easy way to attract people to write down something connected to machine learning. So be careful always to look for something connected with references, but generally they are good. I mean, generally they are pretty good. So it's not that bad still, but it's something if I were you, I will definitely take into account, because
this is why I ask you just one or two reference.
Yeah, for sure. I will give you them.
Yes.
Let me finish with a thing, because the next week I will not be available, because I will be in Namur and I will have lesson there. Yeah. So next week I won't be available. I think if you are fine, we can do on Tuesday, the 25th. Yeah.
Yes, that's fine. Yes.
Okay.
Yes.
So our last lesson, which would be the full learning algorithm, and then something on interpretability. So after we have learned that we have learned, we have a function, but as you can see, it's very tough to understand which kind of function it is, because very often it goes from R to the power of 1000 to R10 or to Z10, and it's it's like very tough to understand which aspect of the input is she like putting her attention on, and so on and so forth. There are some techniques. Some of them I'm researching on right now, and so I will maybe introduce you the spectral analysis of neural network, which is something you can do to understand where information is inside the network.
Okay, very well. Thank you so much. Some other questions from the crowd? No? No, it's people maybe have some other class after also here. It's a complicated schedule.
I actually have a question, Lorenzo. Sorry, because I don't know if you answered it in the previous lesson, but like regarding tests and evaluation loss. Because I mean, the test one is usually like happens to go down up until infinity, pretty much, and the validation one has a minimum, right? Apparently.
Oh yeah. So the validation. If I heard right, you said which is the difference between the validation and the test, right? You want?
No, not really. I wanted to like understand better why the validation test has the behavior it does, pretty much. Why does it have a minimum and it doesn't go to infinity to zero as you improve the testing and stuff?
Why it has a minimum that is not zero?
Yeah, exactly. Why doesn't it have the same behavior as the test loss, but maybe from above, like, or something like that?
Yeah, that's a good question. Actually, the idea is that you will sure mistake more on data that you have not computed the gradient with respect of.
Okay.
So you can then today, I mean, if you have a data that you have been optimizing your function on, for sure your loss function on this data will be smaller than, I mean, you can expect that your loss function will be smaller on that data than on other data that you have you have a computer gradient with respect of. Generally speaking, what will happen is that they will be, if you are doing your things very well, those two losses, the validation and test, will be much closer than the way I will have depicted them. They will start diverging at a certain time. So yeah, I've kind of, maybe I've exaggerated a little bit too much the difference, but generally speaking, what you should expect is that the loss will be a little bit higher on your on the data that you have not computed your gradient with respect of. Makes sense.
Yeah.
You have not in the other case, so it's a bound somehow.
I see. Sure, makes sense. All right, thank you.
No problem.
Great. So if there are no more other questions, we'll see you on the 25th. So okay, so enjoy Namur, say hello to everyone there, and thank you very much for another great lecture. And I'm waiting for this material for reading. Okay.
Yeah, I think at most tomorrow. Tomorrow here. Yeah. I will.
Okay. Thank you very much, Lorenzo.
Bye. Thank you.
Thank you.
Bye.
Well, thank you very much.
Bye, everyone.